Hey everyone, and welcome to today's Explainer. Today, we are diving deep into the hidden, complex, and honestly highly dangerous journey of nuclear fuel. We're going to track the incredible path of this material, from a raw, totally unassuming rock buried deep in the earth, all the way to the blazing heart of a nuclear reactor. The level of extreme engineering required at every single step of this process, it's absolutely mind-blowing, and it's a massive testament to human ingenuity. So, let's get into it.
Right off the bat, I want you to think about something. How can a rock, literally the size of a peanut, power thousands of homes for an entire year? I mean, is it really possible that something so incredibly small can hold that much unbridled energy? Well, yes, but to unlock that hidden power, we have to master one of the most complex, precise, and unforgiving industrial processes on the entire planet. And I do mean unforgiving. Any tiny mistake can trigger a massive disaster. So, how did we even figure this out in the first place?
Well, our understanding of this power built up pretty slowly over time. Back in 1789, a German scientist named Martin Heinrich Klaproth first identified uranium. But back then, it was just viewed as this ordinary, mildly interesting metal. Nobody had a clue about the terrifying power locked inside of it. It actually wasn't until 1896 that French physicist Henri Becquerel figured out that uranium naturally emits radiation all on its own, without any external energy source. That basically kicked off the whole era of radioactivity. Fast forward a bit to 1932, James Chadwick discovers the neutron, and then the ultimate key. In 1938, Hahn and Strassman proved that if you fire a neutron at a uranium atom, it literally splits it apart, releasing a massive burst of energy. Boom! The discovery of nuclear fission.
But here's where we hit a massive scientific roadblock. Natural uranium that we mine straight from the ground, it's not all the same. In fact, 99.3% of it is uranium-238, which is highly stable and, for our purposes, practically useless for generating power. Only a microscopic 0.7% is uranium-235, and it's that tiny sliver, that U-235, that is actually fission-ready. That's the specific isotope that splits and creates the energy we want. So essentially, nature gives us the wrong type of uranium. To generate power, we have to artificially bump up the concentration of U-235. And this unbelievably difficult process is what we call enrichment.
Now, you might remember from history class that during the Second World War, the secretive Manhattan Project, led by scientists like Enrico Fermi and Robert Oppenheimer, raced to enrich uranium to unprecedented levels just to build the atomic bomb. But here's the difference. While weapons require an enrichment level of over 90%, commercial nuclear power plants only need to enrich their uranium to between 3% and 5%. That's just enough to sustain a controlled, steady energy release, not a catastrophic explosion. But because the exact same underlying technology can be used for both, uranium enrichment is still one of the most sensitive, strictly monitored technologies in the world today.
So where do we even get the raw material to start this whole crazy endeavor? Well, uranium is found in a mineral called uranite, but normally it's sitting in incredibly low concentrations. Globally, on average, a ton of rock might only yield about 0.1% to 2% uranium. However, in a few very specific places, like Saskatchewan, Canada, the ore purity can actually exceed 20%. Let that sink in. That is nearly 100 times the global average. It's a massive, incredibly lucrative prize, but getting it out of the ground in those specific geological locations, that comes with some unimaginable engineering hurdles.
Here's the terrifying problem. The richest uranium ore on Earth just happens to be trapped deep beneath a massive, incredibly thick layer of sandstone. And this sandstone acts like a giant, highly pressurized underground sponge that is completely saturated with water. If engineers just went out there and started digging a normal mine shaft straight down into that ore, the sheer water pressure would cause the entire mine to catastrophically flood in a matter of minutes. It takes an already difficult mining job and turns it into an exceptionally dangerous, potentially fatal nightmare.
So how do you conquer this massive underground ocean? Engineers came up with a genuinely brilliant, highly specialized technique called artificial ground freezing. It's exactly what it sounds like. First, they drill hundreds of deep holes right down through that wet sandstone, forming a perimeter around the planned mine. Then, they insert specially designed pipes and start pumping a specialized chemical liquid through them. As this liquid circulates, it literally pulls the heat straight out of the surrounding earth, slowly freezing the groundwater over time. Eventually, it forms a massive, totally impenetrable wall of solid ice deep underground.
This frozen barrier completely holds back millions of gallons of pressurized water, creating an isolated, dry, and safe chamber where the uranium ore can finally be extracted without any risk of flooding. It's like building an ice fortress underground. But maintaining this subterranean ice wall requires some extreme conditions. We are talking minus 30 degrees Celsius. That is the bone-chilling temperature of the highly chilled calcium chloride brine that is constantly 24/7 pumping through those underground pipes. It's this relentless, freezing circulation that artificially holds nature at bay. It literally turns a highly pressurized liquid disaster zone into a rock-solid, safe environment.
Okay, so once the ice wall is secured, the real extraction begins. First, a tiny pilot hole is drilled just to set the exact trajectory. Then, these massive boring machines are sent down to widen the hole and tear into the high-grade ore. But crucially, this entire extraction process is operated completely by remote control. Why? Because the radiation levels of this 20% pure ore are intensely dangerous. Workers have to be kept far, far away from the physical rock, protecting them from both lethal radiation exposure and any potential cave-ins. And just to keep the environment perfectly stable, fresh air is vigorously circulated all the way down into the mine every 20 minutes.
All right, so the ore is safely brought up to the surface. Now what? Well, it gets crushed and ground down into a fine, wet powder that we call a slurry. This is where the heavy chemical processing kicks in. This messy slurry is mixed with some incredibly strong, highly corrosive acids. The acid violently attacks the rock, selectively dissolving just the uranium while letting all the useless rock and impurities just settle out at the bottom. Through this series of super complex chemical reactions, this rough, wet stone is totally transformed into a highly concentrated, purified uranium compound.
But remember that enrichment process we talked about earlier? Well, you can't enrich a solid rock, and you can't enrich a liquid acid. You absolutely need a gas, so that purified uranium compound has to be chemically converted into uranium hexafluoride. Now that sounds intense, right? And it is. It's a highly reactive, incredibly dangerous gas that has to be handled with absolute precision. But converting it into this gas is literally the only way we can eventually separate the isotopes based on their extremely, extremely slight difference in weight. Now the magic really happens. This gas is fed straight into a centrifuge, where the physical separation finally begins. I want you to picture a machine spinning at dizzying, blistering speeds. We're talking thousands and thousands of revolutions per minute. Inside the spinning cylinder, the sheer centrifugal force pushes the slightly heavier uranium-238 molecules all the way out to the outside wall. Meanwhile, the slightly lighter uranium-235 molecules, the golden ticket ones we desperately want, they concentrate right there in the dead center. Now, the difference in mass here is minuscule, almost nothing, so this process actually has to be repeated over and over and over again. They pass the gas through thousands of these cascading centrifuges just to slowly, painstakingly tick that U-235 percentage up to our 3% to 5% goal. Okay, once we finally have our perfectly enriched gas, it's time to forge the actual fuel. Obviously, we can't just pump a highly reactive gas directly into a power plant, so it's chemically converted back into a solid powder, uranium dioxide. Then, these incredibly powerful machines press this powder down into tiny, solid cylindrical pellets. Each one is just about the size of a peanut. But we're not done yet. They aren't quite strong enough. These pellets are then baked in extreme high-temperature furnaces for 24 full hours. This process bakes out any remaining empty microscopic space, vastly increasing both their density and their structural strength. Let this next fact just sink in for a second because it will blow your mind. To understand the sheer, incomprehensible density of what we've just created, a single, perfectly engineered uranium pellet, again, the size of a peanut, contains the exact same energy equivalent as burning 1,800 pounds of coal, or 150 gallons of oil. Just one pellet. All of that extreme engineering we just walked through, the artificial freezing of the Earth, the remote-controlled mining, the acid baths, the supersonic spinning centrifuges, it all culminates in this one incredibly compact little powerhouse. Now, to safely actually use these tiny pellets, highly precise robotic arms stack them end-to-end inside these long metal tubes. And these tubes are made of a very specific material called zirconium. This specialized metal is uniquely, perfectly suited for the insanely hostile nuclear environment. It can easily withstand the extreme heat and the highly corrosive environment of a reactor core. But here's the most important part. It's practically transparent to neutrons.
It allows those vital little particles to pass right through the metal wall completely unobstructed to trigger the chain reaction inside the pellets.
Finally, these tubes are bundled into large assemblies and carefully lowered directly into the reactor core. And this is the climax of the journey. This is where the controlled fission finally happens. When the reactor is fully activated, neutrons are fired straight into the fuel. They pass right through that zirconium, they strike the U-235 atoms, and they violently split them apart. This releases a truly colossal amount of heat, and it also spits out more neutrons, which then split more atoms, creating a perfectly, beautifully controlled chain reaction. All this immense heat boils water into high-pressure steam. That steam violently spins massive turbines, and those turbines generate clean electricity for literally millions of homes.
But there is a solemn reality to this incredible journey. After about a year or so of generating all this immense power, the U-235 inside those tubes is mostly used up. What remains is what we call spent fuel. And at this stage, the fuel rods are lethally radioactive and astonishingly, dangerously hot. The primary chain reaction might be over, but the atomic decay is still very much happening, emitting lethal doses of radiation. The need for extreme engineering definitely doesn't stop just because the power generation does.
To manage this immediate critical danger, these spent fuel rods have to be carefully extracted and instantly plunged deep underwater. They're safely stored in highly specialized pools that are 25 to 30 feet deep. It turns out water is actually an incredible shield against radiation, and it's a highly effective heat sink. These rods literally have to sit in these deep cooling pools for a minimum of 10 years. That entire decade is required just to let their extreme temperature and immediate radiation levels passively dissipate down to a point where they can finally be moved into dry storage containers. As we speak, millions of these spent rods currently sit in pools exactly like this all across the globe.
Which brings us to our final thought for the day. From artificially freezing the Earth, to mining highly radioactive rock with remote controls, to spinning dangerous gases at supersonic speeds and literally splitting the atom just to light up our cities, it is an absolutely breathtaking testament to human intelligence and engineering. But it also leaves behind a real legacy of waste that we have to manage safely for millennia. So the next time you walk into a room and flip a light switch, ask yourself, does the marvel of this extreme engineering outweigh the long-term realities of nuclear waste? It's a complex, challenging question for a deeply complex process. Thank you so much for joining me on today's Explainer. Keep learning, keep questioning, and I will see you on the next one.